Thank you, Rachel. Hi, everyone. Good to see you all here. I'm Aaron Young. I'm now a postdoc at Space Telescope Science Institute, and it's not my slide. Okay, so I would like to use this 5 minutes to tell you about our simulation effort within the Santa Cruz simulation group. So we need merger trees to model galaxies at very high redshift, and they don't exist before the graph simulation. So I took this to my own hand, and you can see these are the number of snapshots stored by these different simulations. Down below, there are three. You're probably familiar with state-of-the-art simulations. Graph is the top row, which we save a whopping of 117 snapshots from redshift 6 to 40. So this gives me some confidence that these extra fine time steps can help us resolve the actual halo merger history all the way for galaxy at redshift 15. So we get history all the way out to redshift 20. So another nice thing about GRAPH is if I were to run this simulation at 100 megaparsec at this resolution, we would break the bank. No computer can do that. So instead of running this in one big simulation, GRAPH really means graph, in the sense of G-R-A-F-T, that's how we pronounce it. So it's a four-tier boxes suite, and it provides halo various mass range, so we can get the merger history of halos across different times, so that it gives us the merger history that we can graph together, so we can understand the full merger history of the very massive halo that we found at redshift 15. Okay, so with that, we naively would like to run the Santa Cruz SAM on these new merger trees and see what happens. Santa Cruz SAM has been around for 2 decades now, 3 actually. Well, 3. Almost 3. So 2.5. And it performs quite well against past HST constraints. And this is just one thing I want to show you. The luminosity functions looks great. So when we run it on graph and compare to the new JWST observations shown in color points here, we would expect them to match quite well. And yet we are about 10 to 100 times fewer than was expected in terms of number density. And we asked ourselves why in the past year. And until we kind of realized that we did not do something perfectly right. So we were storing star formation history in bins of 10 million years, which in those redshift, that is way too wide to capture the young stellar population. Imagine you store all your stars in this wide bucket and call all of them 5 million years old. It turns out that those stars are, well, relatively faint compared to 1 million year old stars. And if we store the star formation history without changing the physics at all, just storing them at a different time, bins, the galaxies become brighter, and it goes from green to cyan over there. And voila, if I put the observation points back on, you can see they're pretty much bang on at redshift 13. I mean, we're still a little short in the bright end, but I blame it on the graph 90 box being too small. So if I were to do graph 2, which is coming right up in the fall, we'll have some bigger box with bigger halos within it, and then we'll probably see them actually. So I guess I'm a little fast, but if you're interested in talking about this more, catch me at coffee.